The last chapter of trig is a very short chapter that is only 2 sections. We are going to go back to triangles, but you don't need to know the unit circle for now. You don't need to know the identities and the formulas for now. You'll need them for the final. And Mrs. Everhart and I were talking during 5th period that you'll need them for AP Calc if you take her class. The CHS Calc class is not heavily reliant on trig, but you will need to remember it for her class, especially the unit circle and the basic identities.
Is there like so it's for like this class we have New York over the summer? Is there?
There is, yeah. It's a pretty large packet.
Oh.
Yeah.
Might as well just do it like the week you get out of school.
No, she suggests doing it in August because the whole goal is to kind of give you a refresher and a review so that you remember it.
Breakdown because we can't remember.
I'm gonna have so much.
You'll be
Like,
able to.
keep your notes, it doesn't matter.
Oh well.
So yes, there is a packet that you'll get for summer, Libby.
Just get the
Um,
notes, people.
If you look at your assignment sheet, I sent out a remind yesterday after school when I realized that I had the same information for Thursday and Friday this week. I don't know what happened, but Friday this week really doesn't exist because we're not doing the same thing 2 days in a row. So Monday's assignment on the assignment sheet is really Friday's assignment. And the test that was originally written on there for Thursday is actually for Wednesday. So everything is a day ahead. So cross off Friday, and then everything on your assignment sheet is just a day ahead of what it's supposed to be at. So as of next Wednesday, we are done with trig until you take the final exam. And really most of the problems, I think 95% of the problems until we get to the very end with limits will not involve trig. So we'll be going back to pre-calculus, going back to algebra. It will be new. Most of it's going to be new pre-calculus stuff. But it might be a nice welcome to some of you. Nice refresher to go back to the algebra and pre-calc. So to wrap up trig, the law of cosines and the law of sines. We're actually learning laws in math. Deal with ways to solve triangles that are no longer right triangles. So pretty much we can only work with right triangles. Even if it wasn't a right triangle in the last part of chapter 4, we forced it to be a right triangle by making a right triangle on the outside of the given triangle. But now, because of these two laws, sine, law of cosines, we don't have to have a right triangle. We can use one of the other, and it's just law of sine, law of cosine. There's not a law of tangent. So we'll be able to use one of the two to be able to solve for the parts of the triangle. So there are application problems that you'll have going back to bearings. So we will use the bearings information. Can you sketch a diagram based off the information that's given? Can you maybe do a little manipulating using alternate interior angles to get an angle here and an angle over here? That would kind of work for you. So that would be some of the homework tonight. So looking at the diagram and trying to get the right angles to work inside of the triangle. Sometimes you get those outside angles. But just a quick review. So the first page here is just a little refresher of what we've done this year and what you've also done in geometry. A little geometry here. But right now, all we've done has been right triangles. Every single thing we've done has been right triangle trigonometry. Even the identities still go back to right triangles. So the right triangles we've worked with, C is usually the hypotenuse because it's the largest side. Angles are uppercase, sides are lowercase. In geometry, you used to use that little angle notation for angle C. You don't need to use the angle notation as long as it's an uppercase letter, it's an angle. A lowercase letter is a side. That's all you need. So you don't need the extra little angle notation there. A and B can be wherever you choose to put them, as long as side A is across from angle A, side B is across from angle B. So your side and angles should line up with each other diagonally. That would have been the notation that we would have used to solve a right triangle. So we're going to look at oblique triangles, which are non-right triangles. There are two types of oblique triangles. It's either an acute triangle, which means there are 3 angles that are less than 90 degrees. All of them are less than 90 for it to be acute. Or it's obtuse, and when it's obtuse, one of the angles will be greater than 90. And only one, because the other 2 that are remaining are going to be less than 90 after you subtract that from 180. So just drawing a little picture here of each so you can kind of see what an acute versus an obtuse triangle would look like. And we'll be working with both. So an acute triangle, again, when you label it as it says for the notation, it's just making sure that you have your angle and side across from each other. You can put A, B, and C wherever you want them to go. So if you prefer C to be at the top, that's fine. As long as angle A and side A are across from each other, same with B and C. And it's going to be based off the information you're given as well. So based off the information, you're going to try and make a triangle at least semi-related to the angles you're given. If you're given an obtuse angle, you should have an obtuse triangle drawn. So usually I make angle C the biggest angle, but you don't have to. So that could be another option for labeling. So the key thing to remember is to have the side of the angle paired across from each other. So the other, like 2/3 of the page, I'd say, maybe a little less than 2/3, is a little review from geometry. But putting in the trig and how it's applying to the geometry from 2 years ago. So when you're solving an oblique triangle, we need to be able to have 3 parts of the triangle to solve for the remaining 3 parts. So we always need 3 pieces of information, and you'll find the other 3 pieces of information. The information that you have then kind of tells you that you should use the law of sines or the law of cosines. So based off of the information from the triangle, do you have 2 sides and an angle? Do you have 2 angles and a side? Do I have 3 sides? That would tell me one versus the other. And by Friday, we'll kind of be able to see why you use one or why you would use the other. But today, tomorrow, and Thursday, we're going to do the law of sines. Just a little refresher, Brandon, what would ASA mean? Angle, side, angle. Do you know why you used angle, side, angle, or any of these in geometry? Like, what was the goal of having angle, side, angle, Brandon?
It's to prove your identities, and angle side angle means that in between 2 angles there's the side is right there.
Oh, I have side, angle, side on here.
So you have to use like the name to figure out what it is. So
Yeah.
2 angles and then the side is the one in between.
Right. So if there's 2 angles, the side is in between the 2 angles wherever they happen to be. The goal is to prove one triangle is congruent to the other. And if you did those little 2-column proofs, that would have been like your last thing. Because of angle, side, angle, triangle ABC is congruent with triangle DEF, or whatever variables, letters they're talking about. So angle, side, angle was one way. The other one with 2 angles and a side would be angle, angle, side. And that just means you have a side that's across from one of the 2. So if we have that information, then we'll be able to use the law of sines. And we're going to do a little proof for the law of sines today as well. In part 2, it says 2 sides and an angle opposite one of those. And I know some of you had Mr. Cummings and Mr. Warnock, and some of you came from next door. What did they say about side, angle? Chelsea?
Like, it's not a thing.
It's not a thing. But you probably learned things in elementary school that at the time you were told it's not a thing. And then later on you learn that it really is a thing.
It's
Well,
just too complicated to teach you.
Yeah, pretty much. It's too complicated to teach it at that point in your life. Guess what? Side, angle, not angle, side. Is a thing. It actually does exist, but it has some conditions. And tomorrow we're going to investigate those conditions. Sounds exciting. Using a protractor and a compass. I still have them. They still exist. So angle or side angle is when you have a side, another side, and an angle opposite one of those. And sometimes it is a triangle. Sometimes it is a thing. Other times it's not. And we're going to see tomorrow why it might not work all the time, which is why in geometry they said you couldn't use it because it didn't really work. But it works sometimes, doesn't work other times. So that's why you were told that. But if I have either of those three setups for a triangle, then we can use the law of sines. The law of cosines only works for the other two options, which would be side, 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 which side, 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 you cannot use to prove triangles are congruent. You can show they're proportional, but side, side, side sometimes doesn't make a triangle either. We'll kind of review why that happens or why it doesn't. And then the last one, side angle side, is when we have the two angles and their included side. Or how about the two sides and their included angle? I can't talk. So pretty much it depends, like when you draw the diagram, you're going to look at it and kind of see what pieces of information you have. And by the end of the week, we'll be able to say, because of this information, we can use the law of sines, or because of the information, we'll have to use the law of cosines. But today, we're only working with the first two options, either angle side angle or angle angle side. So if you flip the page, we're going to do a little proof. So a proof is not necessarily huge, long, and involved, but it uses the information that you've learned, which we're going to use information we learned, and you try and take that information and obviously get to an end point. Our goal is to get somewhere. So the law of sines is what we're going to try and prove. My goal is to show you how it was created. And it really is, it's an easy proof. I wouldn't do a long, crazy proof with you. Mr. Warnock, he's the long, crazy proof guy. Not me. Short little proof. We already did one in the previous, the sum and difference one. We did the proof of the double angle. I'm going to change the angles to A, B, and C. I'm going to change them for next year. Do yours say A, B, and C, or they say alpha, beta, and lambda? I need to change them. So we have these angles alpha, beta, and lambda, or A, B, C. You can rewrite them. I mean, the sides are A, B, and C, so why don't we just make the angles A, B, and C? So when you do a proof, we always have like an end in mind, and the end in mind, so at the very bottom of your page, our goal is to prove or show how the law of sines is created. And the law of sines says A divided by the sine of A equals B divided by the sine of B equals C divided by the sine of C. So that's what our goal is, to figure out how we can get there. So that's why I want you to put it at the end. Using two triangles, or really we just need one. I'm going to use the acute triangle, and we're going to see if we can use that triangle to get the law of sines. So, if we go back to the picture, it says proof. I'm going to use the picture on the left, and what we know from previous trig, a little bit of algebra, to see if we can get that information. So, when you look at a proof, if there's the word sine in a proof, or the function sine in a proof, probably should start with the sign of something because it's in the answer, so we might as well start with it in the beginning as well. And if you look at the triangle that's drawn, this guy over here has the height that's dropped for you. That's called the altitude. And altitude makes a perpendicular angle, makes a 90-degree angle, because we know right triangles. So if you look at the angle on the left, and I told you I wanted you to write the proportion, or the ratio, I should say, for the sine of angle A. What would the sine of angle A be equal to based off of the diagram that's drawn on the acute angle, the acute triangle? So think, what is sine? In SOHCAHTOA, what two variables, letters would represent the sine of angle A? Kate? Yeah, H over B, because sine is opposite, which is side H, hypotenuse, which is side B, because there's like a right triangle on the left side of that entire triangle. So if we do the same thing with angle B, because there's two base angles that are kind of attached or across from that right angle, we can write the sine of angle B, and Kate, the sine of angle B is H over A. So that's information that you know. You might not quite know how to start it, but most of the math classes that I had in college were proofs, and I usually didn't know where to start, so you got to start somewhere by writing something down. And if you look at the answer, try and write something down that's in that answer. So right now we have the sine of A, H over B, sine of B, H over A. What is common with these two equations that we now have written?
They both have
they both have h. And that h is in the same exact spot. It's in the numerator. Brandon, what do you think you could do with that h? Okay. Yeah, so if you have two equations and they contain the same variable, if you solve for that variable that is in both equations, you can then set them equal to each other. So that's how you take two equations and make them one, by taking the variable that's the same or in common. So this becomes b times the sine of a. And the other one becomes a times the sine of b. So that means I can find the height of the triangle by taking the value for the hypotenuse times the sine of the angle that we would have. And then I can find the height. These guys are equal to each other because they both have an h. But because that height is inside the whole outside triangle. So I'm finding the same height just using the left or the right angle. And he said we could set them equal to each other. So b sine a equals a sine b. Well, we're really close to having the law of sines. We just have to rewrite the equation so that we can get it in fraction form. Well, how can we get it in fraction form? So right now we have b times the sine of a times the sine of b, but our goal is to get it as a fraction. Yeah, so you're going to divide this side by the sine of a, taking it to the other side. We'll divide the right side by the sine of b so that we can take it to the other side. Questions? So now we've proven the law of sines for angle A and angle B. We could do a similar proof for angle C. We just have to put the right angle in a different location.
For the law of sines, is it supposed to be C sine or is it? Okay.
Yeah, no, thanks,
I was
Libby.
making sure.
It should be C. So essentially the law of sines says if you take the ratio of the side and its matching angle, not a different angle, set that equal to another side and its matching angle, you can set them as a proportion and solve for any of the pieces. But you need 3 of those pieces, which is why we need an angle, a side, and an angle. So an angle, a side, and an angle so that we can find the distance. So we're going to do 2 examples. One is easy peasy straightforward because there's no application to it. It's just numbers, angles, sides, getting you to see how the law of sine works. And the other one we'll draw a little diagram that has a little bit of application to it. At the bottom of your page, I have it at the top of my screen, it says when using your calculator, which you'll need a calculator. You can't solve it without a calculator. Like, shucks. Such a bummer. You gotta use that calculator again. When using the calculator with the law of sines or the law of cosines, we'll hold all immediate calculations in the calculator without rounding. So that means I don't want you to find the sine of 39 and the sine of 59 and round those 2 answers, plug them into an equation which you're rounding again. Rounding once keeps it more exact than rounding 3 separate times. So plug everything into your calculator, round at the very end. And I'm just changing these. Lambda, I'm making angle C. Beta, it already looks like a B. So we have a triangle with angle C being the biggest angle, 102.3 degrees. Angle B is 28.7 and side B is 27.4. What kind of triangle is this? An obtuse triangle because you have an obtuse angle. So I would like your diagram to be a reflection of the angles that you're given. So we should have some type of obtuse triangle drawn. It's saying that the information that we're given is angle, angle, side, which enables us to use the law of sine. So if I have angle, side, angle, or angle, angle, side, we can use the law of sines. And C is the biggest angle. That's 102.3 degrees. You can place B wherever you choose, above 4 on the bottom right. That's 28.7 And then as long as you place side B across from it, you've labeled your triangle correctly. And then we still have angle A and side A. So without using trig and just using geometry, what can you find? Angle A, yeah. So pretty much just by using geometry, knowing you have a triangle, you can find angle A. Because the whole thing has to equal 180 degrees. And if you subtract the sum of the two angles you're given, we can then find angle A. And it actually works out pretty nicely. Okay. Yeah, so angle A is 49 degrees. So that's geometry, that's not really trig. So now the trig part is how can we use the law of sines. So if you look at the information that's given in your diagram, and you're thinking of those ratios that we're trying to create, Brandon, how do you think the law of sines would work?
We could set up 27.4 divided by the sine of 28.7 equals x over the sine of 1 and 2.3. And then we could solve for side C.
So he's noticing that the information that's given, the pair that's given together is our side B and our angle B. So if we use that information, we're going to use that twice to find both sides. So 27.4, the sine of 28.7. And he's finding side C first, so we don't know side C, but we know angle C is 102.3. So you always need 3 pieces of information because you can only solve for one variable at a time. When you solve for this, again, don't do any extra rounding. I strongly suggest cross multiplying. So it's an equation, you have 2 fractions, you've got a proportion, cross multiply. So 27.4 times the sine of 102.3. And then if I do the other side, I would take C times the sine of 28.7, but to get C by itself, I have to end up dividing by 28.7, the sine of 28.7. So in your calculator, you can place all of that in there. Oops, that's C, not D. But you're cross multiplying to get the variable by itself. So you're taking the 27 diagonally across, you're dividing by the other value because that number will be multiplied by C. Make sure your calculator is back into degree form. You've been working with radians so much, you need to go back to degrees. Libby, what'd you get?
I got C equals 55.747.
747, so I think one decimal place will say 55.8. So using the second proportion, go back to the initial given value. So don't use angle C and side C because you rounded to get to that information. Go back to that initial pair, the 27.4 and the sine of 28.7. Now we want to find side A using angle A, which we calculated to be 49 degrees. So you're using pretty much the same equation, but you're using the other angle. So, Sabrina, do you have a number here? No? Brandon?
43.1.
43.1, and that's it. That's it. That's the law of sines. Questions? So the only way that it could become more interesting would be to make it a word problem and get you to try and draw a diagram. But otherwise, like, the law of sines is pretty basic.
So that's exactly what we did.
Yeah. Tomorrow makes it a little more interesting because we'll talk about SSA. But if you look at example 2, just 2 little examples. You don't really need a lot. This one is talking about Coast Guard. So Coast Guard has two different stations, Station Zulu and Station X-Ray. And it says they are 120 miles apart, but it specifically says that Zulu is west of X-Ray. So what's on the right, what's on the left? Chelsea, who's on the right?
Station X.
Station X. And then 120 miles west is Station Z for Zulu. Somewhere out in the ocean, we have a ship. So there's my ocean. So the next part is where you gotta kind of remember how to draw your angles. The call to Station Zulu indicates that the location of the ship is 40 degrees east of north. Or you could also say north 40 degrees east. That's how we would have written it as a bearing. So you go to your Zulu station, make yourself a little XY axis, and you're at the north, moving 40 degrees in the eastern direction. So okay, that means our inside angle is 50 degrees. And then the other part says 30 degrees west of north, so north 30 degrees west, and that's from X-ray. So if we go to X-ray, we're going north, now we're moving to the west 30 degrees. And Cade, that inside angle is making the top angle 70 degrees. See if you can set up the two proportions to solve for the other sides.
Collected for bond during all lunches tomorrow, Thursday, and Friday. Any questions, please see Miss D in room C39. That's room C339. Thank you.
So the side that we know and its matching angle, we have to keep that as the 120, the sine of 70. And then we have x over the sine of 60. And I'm going to set up the second proportion, 120 sine of 70, and z with the sine of 50. Plug those two values into the calculator. One of them is 100 something. One.
I think X is 110.59.
Yeah, that sounds good. And that's really the distance from Station Z. Because if you look where it's located, that X distance is taking you from Z to the ship. And then the other one, 97.8 or 98.7?
97.8.
97.8. And that's from X-ray. Any questions with using the law of sine or getting those numbers in your calculator? The last little question says if a calculator is capable, or a calculator, helicopter.
It's like an Ethan Burgess calculator last year.
Yeah. A helicopter is capable of flying 200 miles an hour. It's dispatched to the nearest station or the nearest ship. How long will it take to reach the ship? So if you use that common math formula, distance equals rate times time, that would be an easy way to find the length of time that it would take. Because we know the distance from the nearest station is 97.8. The rate is 200. We just need to know the time. And then when you multiply that by 60, it'll get you in minutes. Because I think this is like 0.489. So 0.49 hours, or
29.34 minutes.
Thanks. So your homework tonight Got a couple of triangles you're gonna draw, a couple of application problems. Anybody interested in doing 11 or 47? Brandon, you'll try 11? Yeah? 47? Thanks, Chelsea.